All right, hello everyone, and welcome to our first course in abstract algebra. It's our first meeting of our first course, and hopefully at this time you found our Canvas page, our syllabus, and Charles Pinter's book on abstract algebra, and you saw the first assignment, which was to read the first chapter to sort of set the tone and the pace for the class. Today we have our first little module, and this will give you a sense of the workflow that we'll be dealing with in class, where we'll have these little videos, 10 to maybe 20 minutes at most, where we introduce some kind of concept. Sometimes if they'll have examples we want to show or propositions that need to be proved, these can kind of go as follow-ups. So we'll have a little stack of video tutorials that cover the content, and then I will solve some of the exercises, and then the ones that I don't solve, okay, not all the ones I don't solve, but some of the ones that I don't solve will become the basis for the homework. So in this first module, we're looking at chapter 3 of Pinter, and so we'll be talking about groups. So let's record the definition. A group is a set G with a binary operation, typically denoted by asterisk until clarified otherwise, which is closed under this operation. In other words, given any two elements of this set, their multiplication or their asterisk operation, typically we call it multiplication for lack of another word, will also be an element of this set. We ask that it satisfy 3 axioms. So we have axiom G1. We ask that this star, not a very good star, let's see if we can make it a little better. We ask that our star operation is associative. We remember from Pinter's introduction that this means that while the order of the operations that they are presented matters, it will not matter what order in which those operations are evaluated. In other words, the grouping of these things does not matter. Axiom G2 says that there is a neutral element, sometimes called an identity element, which is denoted by E. An identity element means that no matter what G you pick in the group capital G, this acts by doing absolutely nothing. So in other words, if you're thinking of this as multiplication, then E is playing the role of our traditional multiplication by 1. And then lastly, every element of G has an inverse element. And I know we're running out of room a little bit here, so we'll put this down here. This means that there is another guy, G inverse, with the property that G inverse times G, or G times G inverse, it doesn't matter, will be equal to this neutral identity element that we came up with. Now, I understand at this point in time, this probably feels maybe a little abstract. Well, that's the title of the course, a little bit confusing. Let's see some familiar examples. The most robust source of these are number systems. Because at this point in the game, you guys know probably lots of number systems. For example, the integers. Now, when I'm specifying a group, it's not enough to just tell you the set here. You also have to make mention of the operation. So if I really want to be precise about this, I should clarify that this is z together with the operation plus. And this is already confusing because above we were calling the operation multiplication when we needed to talk about it. But there's no rule that says it has to be multiplication. It can really be any operation as long as it is associative and satisfies axioms G1, G2, and G3. So let's take a moment and convince ourselves that this is correct. So first, good old addition, definitely associative. We know from just our experience doing math that this is true. Of course, is there a neutral element? Yes, there is. The neutral element, or the identity element, is simply 0. Any number plus 0, or the other way around, 0 plus any number, that's always just itself. Lastly, we have to have an inverse element. Now that we understand the neutral element, and of course, we know what addition is, we can understand what it means to find this inverse element. We need to know, given a number n, what number has the property that n plus that number, or that number plus n, make 0. Well, that is just the additive inverse also known as the negative number. Oops. Let's see, can I erase this? Yes, we can. So this deals with the integers under addition. Of course, any other familiar extension of the integers will also work. So for example, we have the nice rational numbers. We have real numbers. And some of you also may know about complex numbers. You haven't seen those yet. No big deal. Of course, addition is not the only operation we can use. We can do multiplication as well. Maybe I should come up here and I should write, this is our example 1. We can also make an example 2. How about q minus 0? So in other words, as a set, all non-zero rational numbers. Under multiplication. Or to be compact, we would write q, and then we put this little star up here to indicate non-zero, and then times for the operation. This is also a perfectly good group. Let's think through the axioms. Let's scroll back up and see them again. We have associativity, the identity element, inverse elements. So associativity, multiplication of rational numbers is associative. I feel I don't have to explain. We're very familiar with good old rational numbers. For the neutral element, it's just 1. 1 times any rational number same as timesing by 1, gets you right back what you started with. And then lastly, the inverse are reciprocals. You give me a rational number. If I multiply by its reciprocal, then this becomes just PQ over QP. Fancy way of writing 1. So you see, this also makes a perfectly good group. At this point in time, one might wonder what the reason for introducing this definition is. And this is a question that will need some time to answer. It will be, well, essentially the essence of the class to come up with lots of important examples of groups, lots of applications of groups. For now, let's just comment that groups are abundant in nature. And by this, I could mean two different things. I mean nature in the sense of the natural world. Physics, symmetric shapes, honeycomb patterns and so on. It might not be clear and to what extent that this is what it even means for that to be a group right now. That's okay. But the other place is in mathematical nature. And what I mean by this is that the objects of mathematical study often have algebraic structure such as groups. And we're going to be seeing quite a bit of both of these throughout this class. At least that's my hope. Now, the best way to get started studying groups is to look for finite groups. Finite groups are better than studying general infinite groups because, well, there's only finitely many elements. And so it makes it easy for us to understand what's happening just by exhausting all the possibilities. So here's our first possibly new example. Integers mod n. And we should probably start by saying what mod n even means. So let's see, what's a good example of this? How about we take mod 12? So we can talk about z, the integers, mod 12, which is often going to be denoted by z mod 12z. This little slash, this guy is read as, oops, sorry about that. This guy is read as mod. And what this refers to is the equivalence class, or more succinctly, the remainder of integers after division by 12. So in other words, as a set, z mod 12z has 12 elements in it. The possible remainders that you get when you divide any number by 12. So here they are. And now in order to make this into a group, we have to endow it with an operation. We'll pick addition. And the rule is to add numbers in this set, we add them like normal, when possible. What about when you add them and they're too big? In other words, you don't land in this set anymore. If, let's call them A and B, if A plus B becomes more than 12, do the division. Get the remainder, that becomes the answer. In other words, 8 plus 10 mod 12 equals 18 mod 12, but that's not in the set here. So what is in the set? When I do 18 divided by 12, the remainder is 6. Maybe a more succinct way of saying it is, if you're more than 12, just subtract 12. That'll land you back in the set. There's a little bit more to it than just this. We'll cross that bridge when we come to it. For now, this is a perfectly good way to endow this list of 12 symbols, 12 numbers, with the structure of a group. Let's check our familiar list of axioms now. Is it associative? The answer is yes. The reason is because what I can do is start by adding up all the numbers and then subtract off multiple copies of 12 if necessary. I know this is quite a bit to look at here, but what's going on? What this means is first we calculate b plus c and subtract 12 if we have to, and then we add a and subtract 12 if we have to. This is saying first do a plus b, subtract 12 if you have to, then add c and subtract 12 if you have to. Well, both of these things could be thought of as just adding up all three of the numbers and then subtracting 12 however many times you have to get back into this set. And so this is a completely fine way of thinking about this. The next axiom we have, the neutral or identity element. I think you guys can see. The identity element is 0. Of course, right? Familiar addition. The interesting part is that the inverses no longer look like you might expect with negative numbers. Inverses are also inverses mod 12. And the way that I like to think about this is to realize that kind of what we're doing here is we're looking at numbers on a clock. I'm going to try to draw you a clock, right? I'm not going to draw the whole clock. I'm not a very good artist, right? Here's our clock. Whatever time it is, when you have to go, 2 hours later, if it's 11 a.m., then you know that that becomes 1 p.m. So in some sense, on a clock, 11 plus 2 is 1. It's the same thing here. The only difference is, in our situation, we don't have a 12. We wrap back around to 0. So it's a little bit different in the sense that, for us, I would put 0 at the top of a clock. Those of you familiar with 24-hour time, for example, military time, probably know that people do that. They say midnight is 0 hours. A little bit of an unusual way if you're thinking about 12-hour time, but perfectly sensible on its own. And so what this means is when working mod 12, you can think of as 0 as kind of being equal to 12 in this set. So when I want to find the additive inverse, I want to do the negative of something, I should use 12 instead of 0 in the sense that if I want to find what number makes 0, what is the, okay, maybe we should write this out. If I want to find, given n, find m such that n plus m equals m plus n equals 0 in this set. Well, because 0 and 12 are essentially the same thing in this set, this is the same thing as asking what value of m makes n plus m equal to 12. And when I say it like that, we can see the answer. that m is 12 minus n. So in other words, the inverse of any element can be found by subtracting it from 12. Inverse of 7 is 5. Inverse of 2, 10. And something potentially noteworthy is that this guy, this set, has an element which is its own inverse. The inverse of 6 is 6. 6 plus 6 makes 12. 12, of course, is not in this set. 12 minus 12 is 0. So I think this is probably a reasonable place for us to start thinking about wrapping up for this first module. The next thing we have to talk about is, well, what ways in which groups can be different from how we are familiar, some slightly less typical examples. And then from there, we'll be ready to start doing our first problems. And I hope that after we go through a couple of these, we start to get a sense of what our intended workflow will be like. So hopefully I'll see you all in just a few moments.